Today, we're going to pull back the curtain on what really makes your computer feel snappy or, painfully slow. We're talking about memory. And believe it or not, the whole story really kicks off with something we've all experienced.
You know that feeling, right? Staring at a loading bar, just waiting and waiting. But what you're actually watching is your computer in a flat-out sprint, frantically moving huge amounts of data from point A to point B.
Here's a good way to think about it. Your computer has this giant library. That's its long-term storage. And then it has a tiny but super fast workbench sitting right next to its brain. Before it can do anything, it has to run to the library, grab the right books, and slap them down on the workbench. That whole trip, that's your loading bar.
So why bother with two separate spots for data? Why not just have one? Well, it all boils down to a fundamental trade-off in engineering. It is basically impossible to build one type of memory that's gigantic, ridiculously fast, and cheap. So because of that limitation, we get something called the memory hierarchy. The two big players in this story are your solid-state drive, or SSD, that's our library, and your dynamic random access memory, or DRAM, that's the workbench. The SSD is for keeping everything safe and sound forever, while the DRAM, it only holds what the computer's brain, the CPU, needs to use right this second. And this table really lays out the differences perfectly. Your SSD has a massive capacity and remembers everything, even when you turn it off. DRAM is way smaller and forgets everything as soon as the power's cut. But the most important difference, the real game changer, is that last row, access time. Okay, check this out. An SSD takes around 50 microseconds to find a piece of data. DRAM takes just 17 times nanoseconds. That's not just a little bit faster. It is an absolutely staggering 3,000 times faster. And this quote just hits the nail on the head. Making your super fast CPU wait for data from the SSD would be like asking a super fast jet pilot to wait for a package being delivered by a tortoise. It's just a non-starter. And that's exactly why we have that loading bar, to load everything onto the jet first. So how on earth does DRAM pull off these insane speeds? To get that, we need to zoom in. I mean, way in. We're going from the memory stick you can hold in your hand all the way down to the microscopic city that lives inside a single chip. So first, let's just look at the big picture. The DRAM sticks have the best real estate in the whole computer. They plug in right next to the CPU, and they're connected by these dedicated, super high-speed data highways on the motherboard. That direct line is absolutely crucial for that near-instant back and forth. Now, let's go inside one of those chips. What you find is this incredibly organized grid system. It's broken down into these independent sections called banks, and each bank is just a massive grid of rows and columns. Seriously, think of it like a perfectly planned city, where every single bit of information has its own unique address. And what do we find at each of those little intersections? What is the one fundamental thing that this whole city is built out of? For that, we've got to zoom in one last time to find the true heart of memory. It's called a 1T, 1C memory cell. It's this beautiful, simple little device, just a few dozen nanometers across, and it's made of only two parts, one transistor and one capacitor. Your computer's working memory is made of billions and billions of these little guys. So, how does this tiny little duo hold information? Well, it's pretty brilliant. The capacitor, it's like a microscopic bucket that holds electrons. If that bucket is full, that represents a binary 1. If it's empty, it's a 0. And the transistor, it's just a gatekeeper that opens up to either check if the bucket is full or to fill it up or drain it out. Simple as that. So with billions of these cells, the memory chip is always humming along, doing three essential things over and over again at just mind-boggling speeds. These three operations are reading, which is just checking the state of a cell, writing, which is changing that state, and refreshing. And let me tell you, that last one, refreshing, is absolutely critical. See, the problem is that these tiny little transistors aren't perfect gatekeepers. They leak a little bit of electricity. So without a constant refresh cycle that goes around and tops off all the capacitors, every single one would drain away and turn into a 0 in just a fraction of a second. This is why it's called dynamic RAM, and it's why it loses everything when you turn the power off. Okay, so let's zoom all the way back out. We've seen the nanoscopic switches, we know how they work, but what does all of this actually get us in the real world? It gets us this. A modern stick of DRAM can handle up to 4.8 billion requests to read or write data every single second. And it's doing that while constantly refreshing its billions of cells so it doesn't forget everything. The scale of it is it's hard to even wrap your head around. And that is the payoff. That's what finally gets rid of the tortoise. This incredible speed is what lets your CPU get the data it needs instantly. And it's what makes everything from gaming in complex 3D worlds to editing high-res video feel smooth and responsive. So, at the end of the day, DRAM solved a massive speed problem. It really is the supersonic jet for our computer's brain, the silent hero behind our entire digital life. And that leaves us with one last question to chew on. Now that our memory is this fast, where's the next tortoise hiding in our systems? What's the next great bottleneck that we need to solve?